Hey, good morning, class. Um, Obviously, I am not there today. I'll be out for a couple days. Hopefully, I am back by Thursday morning. So, the first thing I would like to do, and you should have your combined gas law worksheets out so we can go over those. We're going to go over every problem, and then feel free to pause it as we go through if you need to get caught up or if you want to see something, or obviously go ahead and re-watch the video. So the first question on the combined gas law worksheet is asking you to see how volume is affected based on the factors that are mentioned. So if you increase the pressure, the volume should decrease. That's Boyle's law. If you decrease the temperature, the volume should decrease. Charles's law. But if you decrease pressure, the volume should go up. And if you decrease the temperature, the volume should go down. So at that point, we are unable to determine what is actually going to happen because they're going in opposite directions. For letter D, if you increase the temperature, obviously volume is going to go up. And if you decrease the pressure, the volume is also going to go up. So in that case, we have an increase in the volume. For number 2, we're seeing how pressure is affected. If you increase the volume, we should have a decrease in pressure. That is Boyle's law. If you increase the number of particles, now think about the tire that we've been talking about in the wintertime, how we should always add air. So if you have less pressure, we add air to it. Therefore, that's going to add the number more particles to it, which is going to increase pressure. If we decrease the temperature, the pressure should decrease, Gay-Lussac's law. And if you decrease the volume and decrease the temperature, we should have an increase in pressure. For letter E, if you have an increase in temperature and a decrease in the volume, our pressure should go up as well. But for letter F, if we decrease the number of particles, that means the pressure is going to go down. Less particles, less collisions. And if you increase... Sorry about that. If you increase the temperature, the pressure should go up. So now we have a decrease in one thing, an increase in another. We're unable to determine what is actually going to happen to the pressure. We would have to have numbers to plug into the combined gas law to actually figure out what is going to happen in that case. Moving on to number 3, here we actually had to use the combined gas law. You should have gotten 2.19 atmospheres. Remember, you always use sig figs, and notice that you always write your units in there. Make sure your units cancel out, and you're left with whatever unit you're looking for. In this case, it was atmospheres. Moving on to number 4, you should have 110 milliliters. A lot of you may have just put 107 milliliters. The reason why it's 110, we need 2 significant figures. It's not because of that 24 degrees Celsius or the 5 degrees Celsius. Remember, we added the 273 to it. It is the 740 millimeters of mercury that only have 2 sig figs. So our answer should only have 2 sig figs, and 110 milliliters would be it. For number 5, we were looking for the temperature, the final temperature, and you should have gotten 237 Kelvin. Remember, no degree symbol with that, it's just K. And you should also have 3 significant figures in that problem. For number 6, we now have a volume that we're looking for, and that volume should be 203 milliliters. Again, 3 significant figures. If you look at all of those, the 270 point Kelvin is going to have 3 sig figs in it. And it did say a gas at STP. Remember that STP is going to be 1 atmosphere, and the temperature is going to be 273 K. All right, so if you have any questions on that, we can still go over that on Thursday when I get back. If not, go back through and you can see the work done if needed. So right now, I would like to go over the ideal gas law. So at this point, if the notes have not been passed out, please pause it and pass out the notes. And let's get started about the ideal gas law. So what is the ideal gas law? Well, it actually relates pressure, temperature, and volume along with the number of moles of an ideal, or what we call a perfect gas. Now, what are the number of moles? What does that mean? Well, remember a couple of weeks ago on October 23rd, I wished you guys all a happy mole day. And the reason why that was mole day is because of that number 6.02 times 10 to the 23rd. And on October 23rd, we celebrate it because of its 10 to the 23rd power. But what did I say? What was that number? And it had to do with the number of particles are in a certain mole. It's like 12 eggs in 1 dozen. It's like 500 pieces of paper in 1 ream. It's like 5,280 feet in 1 mile. So a mole is just another quantity that we can take a very large number and make it smaller, more manageable to deal with. And since we are talking about little particles, and there's lots of them, it's easier to talk about in 1 or 2 or 3 or 100 moles than it is talking in times 10 to the 23rd, 26th, 28th power. And that's a lot of zeros. So the number of moles is really the number of particles that we have. So what the ideal gas law really is the modified version of the combined gas law to contain those moles of a gas, which we symbolize with the letter N. The number of moles of a gas is going to be directly proportional to the number of particles and the volume of the ideal gas. So what is the ideal gas law equation? PV equals nRT. A lot of people call this the Piv-Nert equation. The Piv-Nert equation is your pressure times your volume is equal to the number of moles times R, which we haven't talked about yet, and T, which is temperature. So what is that R value? Well, actually, sorry, got ahead of myself. Remember that, and actually you don't know this, so know this, remember this from now on, that 1 mole of a gas occupies 22.4 liters. So always, at standard temperature and pressure, 1 mole of a gas is always going to be 22.4 liters. At STP, pressure can either be measured in 101.3 kPas, it could be 1 atmosphere, or it could be 760 millimeters of mercury. Those are your standard pressures. And your standard temperature, remember not using Celsius, is going to be 273 Kelvin. So I said about that letter R. That letter R is going to be a gas law constant. So we're going to use 3 different values to calculate the R value for the ideal gas law. Why are we using 3 different values, or 3 different R values? It's because there's 3 different pressures. There's going to be an R value that includes kPa. There's going to be an R value that includes ATM. And then there's an R value that will include millimeters of mercury. So calculating R, if we have PV equals nRT, to solve for R, all we have to do divide by NT, right? So we have PV divided by N over T. So we have 101.3 kPa times the 22.4 liters, or divided by 1 mole, which is also divided by 273 Kelvin. That calculates to be 8.31 liters times kPa over moles times Kelvin. Yes, you have to write all 4 units. Notice that none of those units canceled out. So whenever you do these problems, you must write 8.31 liters times kPa over moles times Kelvin. I am sorry, but that's just how it works. So the R value for the atmospheres is going to be 0.0821 liters times atmospheres over moles times Kelvin. Notice that the numbers are different because now we're using 1 atmosphere and not 101.3 kPa. And then the last one deals with our millimeters of mercury. So we have 760 millimeters of mercury is our standard. So we're going to multiply that by the 22.4, divided by the 1 mole, divided by the 273, and you get 62.4 liters times millimeters of mercury over moles times Kelvin. You don't necessarily need to know how to calculate those. I'm just showing you that's why we have it that way. It's important to kind of know the background to it, how those numbers were calculated, but you will be given those numbers on a test. Remember that gas law information sheet I passed out for the quiz? You will have that exact same one that has the R values on it. Okay, moving on to some examples. Oh, I guess one more thing I forgot to mention, if you haven't figured it out yet, when you're using the ideal gas law, we always have to use Kelvin, just like the other gas laws, but we're also using liters. Because of that 22.4 liters, in order to cancel out the liters, all volume must be in liters. And give you a little hint, all your volumes will be given to you in liters, so it shouldn't really matter. Everything will work out. So the first example, you want to determine the volume occupied by 0.582 moles of a gas at 15 degrees Celsius if the pressure is 81.8 kPa. So go ahead and fill in your boxes, 81.8 kPa. The 288 Kelvin, how did I get that? Well, I added 15 to 273, got 288 K, and my number of moles is 0.582. And then the R value, we got to look back. We're going to use the kPa, so it's going to be 8.31 liters times kPa over moles times Kelvin. And again, write out those units, please. Now we want to solve for volume. And since the equation is pretty easy, PV equals nRT, you're going to be solving for PV, N, or T at some point. All you have to do is divide by the ones you don't need on that side of the equation. So in this case, I want to solve for V, so I divide everything by P. So you get volume is equal to nRT over P. Plug in the numbers, 0.582 moles times 8.31 liters times kPa over moles Kelvin times 288 Kelvin. And sorry, the K got cut off. And we're going to divide that by our 81.8 kPa. That will give you a total volume of 17.0 liters. Remember, all volume measurements are going to be in liters, and that's because of that unit that we have for that R value. And we want to make sure that we have the correct sig figs, and there are 3 sig figs in our problem. So there are 3 sig figs in our answers. Okay, example number 2. So one thing that I forgot to do was put in there what pressure do we want to actually convert it to. So we're going to convert it to ATM. It says what pressure in ATMs is exerted by 0.45 moles of a gas at 25 degrees Celsius if the gas is in a 0.650 liter container. So the pressure we don't know. The temperature is 298 Kelvin. We added 273, as you can see on the screen. The volume is 0.650 liters. The moles, which is our N value, is 0.450 moles. And the R value is 0.0821. And I'm sorry I didn't write my unit there. And that unit is going to be liters times atmospheres over moles Kelvin. I wrote it in the problem, though. So we have PV equals nRT. You're going to end up dividing by V to get P by itself. So you get 0.450 moles times a 0.0821 liters atmospheres over moles Kelvin times the 298K divided by 0.650 liters. When you calculate that, you should get 16.9 atmospheres. Now, what if I wanted to figure out what the pressure is going to be in kPa or millimeters of mercury? Do you have to go back through and change the R value in that problem? You could. But I did it a little bit simpler way, I think, where I just did a quick conversion, which is going to be taking the 16.9 ATM, which we just calculated, and multiplying it by the 101.3 kPa and getting 1,710 kPa, or taking the 16.9 ATM and multiplying it by 760 millimeters of mercury and getting the 12,800 millimeters of mercury. So remember that on your test, you are going to need to know the ideal gas law, the combined gas law, Boyles-Charles, and Gay-Lussac's, along with doing those conversions like they're on this problem here. The test should be on Friday. At some point, Mrs. Stay from across the hall may come over and answer some questions either today or on Wednesday to maybe help you guys out if you need it. Feel free to send me questions on Remind if you would like to about chemistry. I will try to get back to you as quickly as possible and try to answer it. I may have to do the problem or send you a picture of it. I don't know. But I'll do my best to answer the questions that you have. And again, I should be back on Thursday. It is doctor's orders that I am out. So with that being said, I hope you guys have a great day. Enjoy this time away from me, I suppose. And then have a great day and good luck with this, and we will get through this. And again, the test may be Friday or I may push it back. It all depends on how well you guys are doing. Have a good day, guys.